This is the opening lecture for chapter 23, which covers electric potential, that is, voltage. A lot of introductory students struggle initially with electric potential. So then therefore I'm going to describe it to us first, not in the context of electric fields, but instead in terms of gravity field. So let me describe to you first of all what is meant by gravitational potential. Okay, let's say that we examine the Earth's gravitational field near the surface of the Earth. Of course, it's constant, and so then therefore we have a series of field lines that are just pointing straight down towards the surface of the Earth. So let's say it right here is the Earth's surface. And then here are some field lines for the gravity field, like so. And the gravity field here in vector form, we'll just write as G. Okay, now let me pick two different heights above the surface of the Earth. Let's say that right here is a height A, where this height is perpendicular to the field lines. Right here is a greater height. We'll label this as B, and the heights themselves I'll label here as HA and HB. And then let's say that I have an object, my marker for example, and the object has mass M. And then let's say that I take the marker and I place it anywhere along this height above the surface of the Earth. In doing so, I do work against the gravitational force, therefore I give the object some potential energy, mgh, in this case mgha. So if I take the marker and I place it anywhere along this dotted line, that is along this height here above the surface of the Earth, I give it the same amount of potential energy. However, let's say that I just want to describe the height itself above the ground without bothering having to talk about the marker itself. In other words, if I just take this height here above the ground and divide out by the marker, what I'm describing then is referred to as the potential to have potential energy, which we just shortcut, if you will, and describe as, in this case, gravitational potential. So in other words, if I take the marker and I place it at this height above the desk, it has the same potential to have potential energy. Therefore, I don't even have to bother talking about the marker itself. I just want to describe the height here above the desk. A height above the desk, anywhere along that height, has the same potential to have potential energy, which we just shortcut, as I said, as gravitational potential. Here's then how we describe this mathematically. Okay, first of all, let's say that I lift the marker from point A to point B. So then therefore there's a change in gravitational potential energy as we go from A to B. So the change in gravitational potential energy would be mgHb minus mgHa. Let me go ahead and subtract out from this the mg. So, okay, now this is change in potential energy as I go from A to B. What do I do if I just want to describe the heights, if you will, from A to B without bothering to talk about the marker? Well, what I do is I take this quantity here and I just divide out by the mass of the marker, like so. This right here, this quantity right here, if you will, is referred to as a change in gravitational potential. It's a change in the potential to have potential energy as we go from point A to point B. The easiest way to think of it is that essentially what it's describing here is just a change in height. This height here has a greater potential to have potential energy than this height here does. Therefore, there's a difference between the two. So these dotted lines right here represent what are referred to as equipotential surfaces. In other words, anywhere along this dotted line, in other words, at this height A here above the ground, the marker would have the same potential energy. Therefore, the height itself has the same potential to have potential energy. This is referred to as an equipotential surface. Now here's an easy way to wrap your head around this concept of an equipotential surface. Because it actually shows up in a specific type of map, what is called a topographic map. A topographic map is a two-dimensional map, but it shows relief. It shows elevation, for example, and it shows depth, say when you're talking about the ocean floor. And then in a topographic map, you're always going to see what are called contour lines. The contour lines are equipotential surfaces. So for example, imagine looking at a contour map or a topographic map that shows relief and elevation, where each of the contour lines are separated by 10 meters. And then you could describe, for example, a mountain peak using those contour lines. Okay, I provide for you in today's folder a screencast of equipotential surfaces in the context of topographic maps. Go ahead and pause this lecture here at this point, and please take a look at that screencast. Okay, so now that you've seen that screencast, this will hopefully give you the idea of what is meant by an equipotential surface. It's basically the same height, if you will, above the origin. So at a height of 10 meters on a contour line, that's the same potential to have potential energy, and then 20 meters is the same potential to have potential energy, and so on, okay? Okay, now how do we describe this quantity here, change in gravitational potential, in the context of the gravity field? Well, we go back to chapter 8 to do so. Okay, recall that change in gravitational potential energy is equal to the following. It's equal to the negative of the work done by gravity, where the work done by gravity as a line integral is the following quantity, where the force itself, of course, is just mg. And then in terms of the notation on the diagram above, imagine lifting the object from point A to point B. So then therefore, generically, I'll just refer to the limits of integration here as point A and point B. Let's go ahead and take this quantity and just divide out by the mass itself. And that then gives us the following expression. From point A to point B. In general, this quantity right here is the change in gravitational potential. The units of gravitational potential are joules per kilogram. But once again, the easiest way to wrap your head around it is that it's essentially just describing a change in heights from one contour line to another, for example, on a topographic map, from 10 meters above the ground to 20 meters above the ground, and so on. That's once again the easiest way to wrap your head around what is being described as a change in gravitational potential. And now what we'll do is we'll extend this to describe it not in the context of gravity, but now in the context of an electric field. And then therefore we will end up with a description of change in electric potential. Change in electric potential is also known as voltage. Okay, so let me go ahead and erase this for gravity. I'm just going to reconstruct this diagram here in just a moment. And now let's describe it all instead in terms of electric potential. So what I'm going to draw here is a constant electric field. The easiest way to think of it is in the context of a parallel plate capacitor. So let's say that right here is a positively charged sheet. Right here is a negatively charged sheet. And then recall from earlier in Gauss's law that in the space between the two plates of a parallel plate capacitor, you have a constant electric field. In this case, it will point downwards on my diagram, away from the positive and towards the negative. So I'm trying to keep this diagram here consistent with what we saw earlier when talking about the gravity field near the surface of the Earth. Okay, so here's my electric field, like so. Drawing in some field lines. And this right here is my electric field, E. And then once again, let's think of it in terms of heights, equipotential surfaces. So right here, we'll say as a height A. Right here, we'll say is height B. And then what we do is we take a positive test charge. Recall from earlier when talking about Coulomb's law, for example, in chapter 21, that by definition, we always think of the test charge as positive. So we have a positive test charge. That positive test charge we'll just label as Q. And then let's say that I take that test charge Q and I place it anywhere at this height, if you will, above the bottom plate. In doing so, I do work against this electric field, therefore I give the object potential energy. However, anywhere along this equipotential surface here of height A, if you will, above the negative plate, the charge itself would always have the same potential to have potential energy. So then therefore, let's take the potential energy and just divide out by the charge. When we do, we end up with a difference. In this case, as we say, go from A to B, a difference in electric potential. Here's then how we describe it. Once again, think of it in the context of taking a positive test charge and now lifting it, if you will, from height A to height B. In doing so, there's going to be a change in potential energy, in this case, electric potential energy. In terms of an integral, we would describe that in the following way. Change in potential energy is equal to the negative work done by the electric field. Like so, where the work done by the electric field is the integral of the force, the electric force that is, as we say, go from point A to point B. Let's go ahead and replace the electric force now, however, with the test charge Q multiplied by the electric field E. And then once again, just generically in terms of the limits of integration, we're going from point A to point B on the diagram. So now let's go ahead and label this here as A and B. Let's then describe the potential to have potential energy, the difference in that as we go from A to B by now taking this quantity and just dividing out by the charge Q. That then gives us this. Incidentally, at this point, there's a notation change. Typically, when describing electric potential, the infinitesimally small displacement vector is not labeled as dr. Instead, it's labeled as dl. This is just a notation change that occurs here in the context of electric potential. So the dl right here is once again just an infinitesimally small displacement vector. It's the same thing as dr as we've seen earlier. Once again, however, it's just a notation change. This quantity right here is now the difference in electric potential, the difference in the potential to have potential energy when we go from point A to point B on the diagram. So difference in electric potential. This is also referred to, by the way, as voltage. So we now have a new quantity here. This new quantity is potential energy, or change in potential energy, that is, per charge. So it's measured in terms of joules per coulomb. A joule per coulomb is given its own name and symbol. It's referred to, of course, as a volt. So the units of joules per coulomb is a volt, which is just typically referred to as V. There is some additional notation, however, that is used to describe this quantity, specifically the left-hand side of the expression. You'll see the left-hand side of the expression written a couple of different ways depending upon the context. So here on the left-hand side, we now have change in potential energy as we go from point A, the initial point in this calculation, to point B, the final point in this calculation. This quantity here then on the left-hand side of the expression is now written in the following way. The potential at B minus the potential at A. This is then equal to the integral here on the right-hand side of the expression. Like so. The final point is point B on the diagram. The initial point is point A on the diagram. You'll sometimes see this guy here on the left-hand side written like this. VBA means the same thing. Sometimes you'll see it written like this, delta V. It depends upon the context of the situation. Later on, when talking about electric circuits, for example, there will also be some additional notation changes. So once again, change in electric potential is equal to ultimately the following integral. The easiest way to think of it, once again, is always just in terms of change in heights, from height A to height B. Anywhere along height A, the positive test charge would have the same potential energy. Therefore, height A has the same potential to have potential energy. It's the same value of electric potential. Now, throughout my diagrams here, by the way, when describing electric potential and earlier gravitational potential, I've been describing the equipotential surfaces, for example, as always being perpendicular to the field lines. Okay, you may want to, by the way, once again, write in that these are equipotential surfaces, like contour lines on a topographic map. The reason why equipotential surfaces are perpendicular to the field lines themselves has to do with this dot product. So imagine calculating this dot product, for example, when we take the positive test charge and move it from here to here. When we do, there's a 90-degree angle between the electric field and the displacement vector. From the dot product here, cosine of 90 degrees is equal to 0, so then therefore no work is done by the electric field when you step in a direction that is perpendicular to the field lines. Therefore, that direction perpendicular to the field lines is an equipotential surface. So the equipotential surfaces are all perpendicular to the field lines for that reason. Okay, in the next portion of the lecture, in the next video, then we'll start to go through some practice calculations of what happens when charges fall through an electric field. That is, they fall from one value of electric potential to another.